invited speaker, Ridin Spinoza from NASA Goddard, and he will be talking about synergetic LiDAR and polarimeter aerosol retrieval performance under complex conditions, exploring the cost of imperfect particle shape assumption.
Thanks, Oleg. Do I have 10 or do I have? You have how many? 15?
Yeah, last we have. There is one cancellation.
No, it's on the schedule. It's 15. All right. Hi, everyone. So yeah, I'm going to be talking about some work we did exploring the impact of different particle shape models on retrieval performance, both spheres and spheroids, but we've also looked at the TMAU 2020 dust database that was recently released by Ping Yang and Masaseto. Okay, so we know that polarimetric measurements provide new insight into aerosol properties, more information than intensity measurements alone. And as a result, we're launching quite a few high performance polarimeters over the next decade. And these are motivated in part by quite a few very nice theoretical studies that show polarimeter retrieval performance under a variety of conditions and try to quantify that. But one thing we haven't looked at very carefully is what happens when you have forward model error in your inversion. So if you do something like assume the wrong particle shape, something that's not consistent with the observation. So that's what we're hoping to look at here. That could be very important in future polarimeters where the accuracy is much higher. You're going to have more sensitivity to that. And it's also going to be really, really important in the AOS mission where we pair a polarimeter and a LiDAR together because of the observation geometry of LiDAR. It can be very sensitive to particle shape. So currently, dust, particles in reality are very, very complex, but for a variety of reasons, we have to simplify them in the retrieval. We don't have a great picture of what they look like and their relative distributions. Computationally, it's prohibitive to simulate a whole lot of these particles. It's just not feasible. And remote sensing retrievals don't contain enough information to retrieve all those details anyway. So we try to simplify them by finding some relatively simple model that reproduces the optics in the space or the measurements that we care about. So here we're doing basically a truth in, truth out retrieval simulations, the same thing that Anand was showing earlier. We forward simulate the measurements with GRASP, add some noise to them, and then form retrievals on the simulated measurements and compare that to what we use to derive the inputs or derive the simulated measurements. And we can do this both with the same forward model as the model using the inversion, or we can do it with different shapes. So forward simulate with spheres and invert with spheroids, or TMAU 2020. So we do this for 3 instruments to start out. MISR, which we heard about earlier, basically a MISR with an extended spectral range to match MODIS, and then a polarimetric MISR plus MODIS, actually plus a UV channel too. And we do it over a bimodal size distribution for a range of kind of realistic AODs, and SSA is actually fairly low. SSA is a little absorbing. So this is just summarizing those results. I've contextualized them against the uncertainty targets that were presented by Mashenko in his 2004 paper for climate studies, just to kind of put them all on the same scale. So each one of these bars represents the distribution of error for that particular measurement and that particular variable. And as you would expect, as you add more information to the measurement, you get better retrievals. Some parameters, polarization helps more than others, again, as we expect. The real refractive index and the effective radii both get pretty big boosts when you add polarization, and that kind of is required to push you over the threshold of the target that Mashenko specified in that paper. So polarization is very important in there. So then we reran these simulations, both using, in all cases, we use spheroids in the fine and the coarse mode forward calculation, but we inverted either with only spheres in the fine mode or only spheres in the coarse mode. And as you would expect, assuming spheres in the presence of non-spherical particles in the coarse mode degrades the retrieval performance pretty significantly, not just in the polarimeter, but even in the intensity only miser and miser plus modus. But what we found that was a little more surprising was that even in the or in the polarimeter retrievals, that even if you just assume spherical particles in your retrieval of the fine mode, but you still represent the coarse mode by the spheroids that were used in the forward simulation, you still lose some accuracy in your retrieval, especially in real refractive index and effective radius, those parameters that polarization really helped you with earlier. So there's a pretty big measurement space here, right? You have several different measurement types in a polarimeter, Q, U, and I. We also are interested in HSRL, so there's another few measurements. They're done at different wavelengths, different angles. So we wanted to find a way, kind of a single parameter we could use to quantify how well one forward model, say with spheres, matched another forward model, say with spheroids. So here I'm showing that example. The blue areas represent basically areas where the so what I'm plotting here is kind of like it's a chi-squared, but not between measurement and fit, but between two forward model calculations, basically. So it's the difference between the forward models normalized by the measurement error. So the dark blue regions represent spots where the difference between the two models is less than the measurement error. White is it's roughly equivalent, and red, the difference between the models is significantly more than the measurement error. So we see basically the same thing we saw in our retrieval simulations here, that in the fine mode, there is a little bit of sensitivity to the particle shape, but not a whole lot. But as you get into coarse mode, the difference between spheres and spheroids grows pretty quickly, and it is a much larger than the measurement error that we expect from these instruments. And this is all done with a monomodal log normal test case, and we hold the AOD constant between the two. You could also hold the concentration, but we decided the AOD would be a more apples to apples comparison. So now we've integrated this TMAU DUS 2020 database into GRASP, and that allows us to do these forward calculations, not just with spheres and spheroids, but also with these hexahedrons. And we go ahead and do that and see that the differences are definitely less between the hexahedrons and spheroids, but not completely negligible, especially in the larger size ranges. So for the polarimeter, the fine mode, there really isn't a significant difference. So earlier we saw that if you try to retrieve using spheres for a scene containing spheroids in the fine mode, it can significantly impact your retrieval. That's probably not going to be the case just between these two different non-spherical particle shapes. For HSRL, it's a little more sensitive to particle shape. Again, this is what we would expect, but it's still in the fine mode. There's not a huge difference between these two. And there's another way to, or we should caveat this saying that it's not obvious how you map the shape of one non-spherical particle against the other. So here we're using volume equivalent radii to make the scenes the same. But it turns out that if you shift the radius of the spheroids to be 20% smaller than the hexahedrons, you actually, you actually get much better agreement in some regions here, although worse in the fine mode. So that's something we need to explore. And Masasato actually had a very nice poster talking about that, and he concluded that effective radius was actually the best metric to compare apples to apples in terms of optical properties. So that's something we need to explore more. But on the whole, we found that no matter how you shifted it, so independent of how you define the size equivalence, the region above 3 microns disagreed pretty significantly between the two particle shapes in both the polarimeter and the HSRL. So we did some retrieval simulations using just the polarimeter. These were done by Grima Regmi. She talked more about them in her talk on Wednesday. But what we find is, in these simulations, if we forward calculate with hexahedrons instead of spheroids, we get similar results when we retrieve with spheres. It degrades the retrieval significantly. Here, we're actually looking at a bimodal distribution, not a monomodal. So there's a coarse mode in here. For spheroids, we find that forward simulating hexahedrons and retrieving with spheroids doesn't actually really impact your AOD retrieval very much. It's still as accurate as it would have been if you'd used the same particle model. But other parameters like SSA and especially real refractive index, which isn't shown here, showed pretty significant biases when we did that. So for AOD, the difference between these two different non-spherical shapes may not matter much, but for the other properties, it seems to. So what we've done so far is just kind of map out the region, the regions of the state space that are dependent on particle shape and, which measurements are most impacted. Now we need to go in and actually look at measurements and then, tune into the areas that have shown the most impact and see if we can train it with measurements, which shape models actually work the best. So there are a few ways we could do that. One really nice way that we haven't started or even really talked to Greg about is the STEER project that Greg Schuster PI'd at Langley. We have extinction, SSA, and a P11 and P12 for a really wide range of dust particles that we could use to test the different shape models. There's obviously also airborne data, HSRL, polarimeter, and polar nephelometer measurements. And then we've also started looking at HARP CubeSat observations of dust to see if perhaps one model produces a lower fit residual than another. But that work is just beginning. So in conclusion, polarimetric measurements provide enhanced sensitivity to a lot of retrieved parameters relative to intensity only parameters, but they seem to be more sensitive to forward model assumptions or to the quality of the retrieval priors. Neglecting non-sphericity in the coarse mode degrades retrieval performance by a very large amount. We expect that. But assuming spherical particles and the inversion of a simulation based on data from fine mode spheroids actually negatively impacted polarimeter performance in a few variables, real refractive index and variables representing size. In forward simulations of polarimeter and HSRL observations, coarse mode hexahedra and spheroid particles produce differences that are significantly larger than measurement errors, especially at sizes above 3 microns. And polarimeter retrievals of AOD actually turn out to be very robust, even if you assume different non-spherical shape models. And I'll stop there. Thank you.
So questions, please. And if you can, then go ahead. Just please ask in micro. But you can say like this. I'm not sure.
I can repeat.
Yeah, great talk. I'm wondering things that
I'm sorry, what was the last? Yeah, so that's what we need to go and look at real measurements for. So we really don't know whether the hexahedra, the spheroid, or some other shape is going to be what ultimately does the best job of reproducing polarimeter, polarimeter LiDAR measurements. But the key takeaway here is that it does. Those are the hexahedrons, and the spheroids are kind of leading, two of the leading models for shape, and their differences between them are significant enough to cause pretty major retrieval errors. So we need to do more investigation and improve the models. It's kind of the main takeaway.
So hey, Ray, very nice talk. So sorry about my voice. So you show the difference of comparing the hexahedral with the spheroid for the retrievals of AOD and SSA, and I found you show that the hexahedral have done a very better job for compared with the spheroid. And can you explain the reason why and explain more behind it?
So here this is all simulated data, and we're forward. The simulated data is calculated with the hexahedrons. So when you retrieve with hexahedrons, they're going to do a good job because they're they were used in the forward simulation. If you were to swap it and forward simulate with spheroids and retrieve with hexahedrons, I would expect that bias in SSA to shift to the hexahedron side, and the spheroids would look very nice.
So in terms of that, how do you tell which one's better?
Again, we have to look at the measurements. We haven't gotten to that stage yet. We're just trying to scope out what we need to explore in order to.
Okay, thank you.
Mm-hmm.
And Reid, I have a related quick question. When you look at the goodness of fit between hexahedral and spheroids, was it significant? Could you fit well or not? I mean,
The fit was pretty good, yeah, even when you forward simulate with one and retrieve with the other. So even though you're not getting the same the same retrieve properties, you do a pretty good job of fitting the curve almost within the simulated measurement error. So it's tricky to tell. You can't, just looking at the fit is not sufficient to know whether your shape model is good enough. It's the takeaway there.
So very nice talk, Reid. So my question is, when you say that you've incorporated these different shapes into GRASP, are these in the public version of GRASP, or these are just what you guys are using internally?
These are what I'm using internally, but
Is there plans
available.
to get them onto the GitHub anytime soon?
They're available from us upon request. Whether they're going to end up on the GitHub is a question for Oleg.
yeah, of course. I mean, if there is interest, and even us, we're interested.
Okay, thank you all.
Thank you. Yeah.
So our next talk will be by Xu Lei. He's going to talk about solving forward and inverse problems for hyperspectral satellite remote sensors using principal component analysis.
Thanks. Do you have a pointer? Anyway, so I can just talk here. I'll use the mouse. Okay, thanks. So first of all, I would like to thank a lot of people who have contributed to this work. It's work for the past decade or two, actually. I just want to say for hyperspectral sensors, they have hundreds to thousands or even tens of thousands of spectral channels. So it is it has a lot of information content in one spectral, but computationally it's very difficult to do the radio transfer full model calculation. And also for the inversion, the dimensionality is too big. So we need to think about how to do that. So So first of all, I want to say about a full model. Okay, in order to properly account for all the atmospheric trace gas contributions to the TOA radiance or reflectance, you in the solar spectral region, you have to do over like 2 million monochromatic calculations in order to do the integration to the instrument function level properly. In the infrared, it's the same thing. So what people do is they reduce the number of radio transfer calculation to the number of spectral channels. So we call it a traditional channel-based radio transfer model. So you reduce from millions to few hundred to tens of thousands. So that's great, but still it's too slow because we have to do multiple scattering and integrate through a homogeneous atmosphere. So the way we are thinking about it, we compress the hyperspectral into principal component domain. So you basically reduce the dimension by a factor of 10 to a factor of 100. So there are two functions of this. First of all, you reduce the noise of your measurement. Secondly, reduce the dimensionality. And thirdly, in the inversion process, you make the inversion process more stable. I will explain that a little bit later on. So I just want to demonstrate with this three figures, three plots. The PC is nothing, mathematically abstract. You can see it, okay? So the definition of super channel is the projection of your hyperspectral onto a set of eigenvectors or principal components. So we call it super channel or PC scores. So the first plot really shows the radiance as a function of a lat long for Chris instrument at the 910 wave number. So you can see the variation globally. The second, the middle plot is the first principal component, the first super channel. So you can see they're highly correlated. The super channel really contains your original spectral information. So, and the third one is the reconstructed radiance from the super channel. You can see the third panel and the first panel are almost identical to each other. So it really says the PCA can really compress your measurement into a dimension much smaller, but retain all your information, spectral information. So go to next slide. So we know, when Yazi was first launched, a lot of people were excited about this PC compression, but they need a full model that can do the super channel radio transfer calculation directly. So in 2004, we developed a principal component-based radio transfer model. The beauty of this thing is, I just want to say the instance of it. So the radiance is proportional to the super channel, but the super channel magnitude is proportional to your monochromatic radiance. So we use the monochromatic radiance as predictor to our super channels. So the beauty of this is we can do radio transfer monochromatically. So you don't have polychromatic assumption, which are not valid. For example, the correlated K, if you have inhomogeneous with multiple trace gases, the assumptions are not valid. But with this PCRTM, everything is physical. It's a physical-based radio transfer model, even though it's in the principal component domain. And I just want to show you on that plot. This is an example in the solar spectral region for OMI spectral region to retrieve the ozone profiles. So originally you have about 1,500 monochromatic points, but if you do PCRT model, you only need to do 14 monochromatic calculations. So you reduce, the computational burden by factor of 10, factor 100. So now, I just want to show you some examples of the how PCRTM has been applied to many sensors. It includes about dozens of sensors, but I just want to show you the calculated PCRTM calculated TOA reflectance with respect to schemaki. You can see on the top left, they agree with each other very well. And then the other two panel are the simulated PCRTM radiance and comparison with MODIS. You can see again, they agree with each other pretty well. The lower three panels are for the thermal infrared hyperspectral data. For Yazi, Chris, and AIRS, the difference between the PCRTM simulated and the observed hyperspectral data are shown on the bottom panels. you can see they agree with each other to the noise level. The red curves are the noise. You can see the agreements are pretty good. And now talking about the inversion, the first equation is the optimal estimation iterative retrieval. So you have a few key variables here, like R is your measurement radius, or in our case, we compress the R into PC domain. So instead of hundreds, thousands to tens of thousands, we typically only use about 120 to 180 PCs, super channels, which are shown in this table. So anyway, now talking about the inversion. So typically the radial transfer equation is nonlinear, and if you want to invert this, we call it a Frame-Home equation of first kind. So it typically is a yield conditioned. What does it mean? If you have a random noise or some kind of a systematic noise, mostly random noise, if you change your random noise a little bit, your solution could change quite a bit. So you will have an ensemble of solutions. So therefore, your uncertainty in your retrieved vector, which is X, will be much larger. So now, if you apply the PCA to the hyperspectral, the first thing you reduce is the random noise. So you reduce the not the computational time, but also the yield condition of your inverse problem. So, and now talking about state vector X, for the infrared hyperspectral sounding, we retrieve temperature, water vapor, like 4 or 5 trace gases. And in thermal infrared, we need about 100 layers. And it just to represent those profiles, you can see at least you need 700 elements for the vertical profiles. That's just too many state parameters in your state vector. So, but you can do information content analysis of your spectral, with respect to each component, what kind of information you have. So that's why we can reduce the eigenvectors to like for temperature to 20, for like trace gas, all the way from 1 to 2. So that way you reduce your dimension by an order of magnitude. So I just want to show you some 2 examples of the algorithm based on the principal component radial transfer model, the PCRTM. The first one is called is a level 2 algorithm. It's called a single field of view atmospheric sounder product. It is different from the operational sounding algorithm in the sense that we use all the spectral channels because we're using the PCA analysis. We retrieve all the parameters simultaneously, like cloud, surface, temperature, water vapor, trace gases. For the operational algorithm, current NOAA and the NASA operational algorithm, they're doing cloud clearing. So they don't do cloud retrieval simultaneously. They remove the cloud from the observed radiance, which will introduce some error because the assumption they made may not be valid in the real world. And then, so the other advantage is we're doing a retrieval for each field of view. So our spatial resolution is about 3 times higher than the operational product. So we, instead of a 45 kilometer now, it's about 15 kilometers. So this algorithm is being transitioned to operational algorithm. Right now it's being kind of almost fully tested at the NASA Sounder SIPS. It's a computer facility at the JPL. And will be transitioned to the NASA Goddard DAC pretty soon, hopefully in January or so. And then we have another product, it's called level 3 product. It's a climate fingerprinting sounder product. Instead of doing retrieval for each field of view, we average the radiance temporally and spatially. So let's say we get monthly mean, and then we do either zonal mean or a 0.5 or 0.5 degree grid. And then we apply the retrieval on those average radiance. So you can imagine this is going to be very fast, okay? But it's going to be physical as well because we use the same radial kernel derived from our level 2 algorithm and apply that to all the sensors. So anyway, the bottom 2 figures shows the the product from the SIPSAP and the ClimFist. So on the right hand side, you see the surface skin temperature using like 20 years of ALS data. So we can easily derive that from the ClimFist data. So I'm almost there. So in conclusion, the PCA is a good way to compress the hyperspectral data. It stabilizes the solution, reduces the noise, and also reduce the ear conditioners. You can also use to compress your state vector if they are highly correlated. If they're not correlated, there's no use of it. And you can use not only PCA, you can use other Fourier analysis, harmonic spherical, or cosine. I mean, anything, it's just a way of compress the spectral. The PCR-TM is fast and accurate. It's physical. So I just want to say in the thermal infrared, the RMS error of the PCR-TM is about 0.02K. It's an order of magnitude smaller than the instrument noise. In the solar spectral region, we're shooting for 0.05% relative to the line-by-line model. So that's it. So let me see. What else? Yeah, that's all I have. So I'll be happy to answer questions.
Hi, very good talk. Sorry, I have to use the microphone. So I have a question about using this PCR-TM for doing retrievals, for example, for cloud or dust aerosols in the thermal infrared. So is that possible for users to manually input the optical properties of the cloud or aerosols by user themselves for these radiative transfer simulations? And if yes, how the PCA methods handle those optical properties?
Okay. Yeah. I mean, to the radiative transfer equation, you just input, you can input the single scattering properties or parameterized. In this case, we're using parameterized cloud properties. So we have effective radius and the particles. I mean, the optical depths at 550 nanometers and then the cloud height. But the cloud shapes are assumed. So that's one way. The other way would be we can retrieve the single scattering property spectral. And again, we can do PCA analysis to compress it into various few components. So that way, not only we retrieve the cloud, we can retrieve the shape of the cloud. So our idea is if we don't fit the spectral well, we would try to maybe get information about the cloud shape from that.
So user do allow to be input their own optical properties.
Yeah. So yeah, that's a little bit more involved, but we haven't really make it operational yet. So thanks.
Thank you.
Okay, thank you. Let's move. And next is online presentation by Men Gao. And it's adaptive data quality control and uncertainty analysis in advancing multi-angular polarimetric remote sensing for PACE mission.
Good afternoon. This is Meng from NASA Ocean Ecology Lab. So thanks Feng and Oleg for organizing this session. Sorry that I cannot make it in person. Here I would like to share our recent uncertainty analysis work for PACE multi-angle polarimeter data processing. I also would like to thank our collaborators and the PACE project for the support. You may be already familiar with the PACE, so which includes 3 instruments. OCI is the ocean color instrument, which is hyperspectral in a wide swath. And the SPECS1 and HARP2 are multi-angle polarimeters complementary to each other. SPECS1 conducts a hyperspectral measurement in a narrow swath, while HARP2 conducts a hyperangular measurement in 4 bands, but in a wide swath as wide as OCI. So our current interest is to process HARP2 data over ocean, which can then be used in synergy with OCI to improve aerosol and ocean color remote sensing. So we know that map measurement have been shown to be very useful to retrieve aerosol, microphysical and optical properties. Several advanced algorithms have been developed to retrieve multiple aerosol and surface parameters. Some of the algorithms have been applied on PACE proxy data. So I won't get into the details here, but you can get more information from PACE website. So our previous work is to develop this algorithm called Maple, which focuses on the inversion of aerosol and ocean parameters simultaneously. The form model is based on the coupled atmosphere and ocean rangefinder model developed by Peng Zhai. And we have been using RSP data to evaluate the retrieval capability over both open and coast waters. So another work we did is to combine RSP aerosol retrievals with SPECS data. In this way, we can derive hyperspectral water-level signals. So this will be a demonstration for the synergy of PACE polarimeters and OCI. So our current work is based on the Maple algorithm, but we have 3 goals to improve. That is in terms of speed, accuracy, and how well we can understand our retrieval. So the speed accuracy part can be improved based on the neural networks, which can be used to represent the form model and their Jacobians. So based on this fast retrieval result, we have been using it to analyze our retrieval performance, so we can better understand the retrieval uncertainties, and in this way to identify gaps for future improvement. So to understand the retrieval performance, we actually look at 2 closures. The first one is we look at the retrieval uncertainties. So we can calculate the retrieval uncertainty from error propagation theory, and then compare with the result we get by comparing the truth data from the synthetic simulations. In this way, we can verify whether error propagation can really represent reality. Another closure is we look at the input uncertainty model for the measurement. So we can compare that with our retrieval fitting residuals and to see whether these 2 are consistent to each other. So let's first look at the retrieval uncertainties. So we simulate the 1,000 sites of synthetic measurement with random aerosol and ocean properties to conduct this study. So the real uncertainty error are computed by comparing the retrieval result with the truth from synthetic data. So here we are using AOD as an example. We can also sample random errors from the error propagation uncertainties, and then we can compare directly their statistical distribution. So in this example, we can see the real uncertainties have a slightly larger values at the tail, but overall, their distribution are comparable to each other. We can then extend this study to study the impact at the different aerosol optical depth range. So here we have the uncertainty for AOD, for the water-leaving signals, and also for the class A concentration in the ocean. We can see the uncertainty is generally increased with AOD, but the real uncertainty is slightly larger than the theoretical one. That means there's a further room to improve. So besides study the retrieval uncertainties, to understand the retrieval performance, we can also check the measurement uncertainty and compare with the fitting residuals. So in this example, we have the error measurement, and in this thing, there's our transparent cirrus cloud here. So if we look at the fitting result and by compare the measurement with the form model, we can see there's a gap here, and we can also compare this gap with our uncertainty model. We can see there's a large ratio here, so we can use this ratio to identify where the anomaly is. That is where the cirrus cloud having to be there. And here we are showing you how the impact of cirrus cloud on the retrieval result. And on top we have the impact. We have the cirrus cloud here, so we can see our retrieval AOD have a peak here, and but after we remove those angles impacted by cirrus cloud, and we are using other angles to the retrieval, we can see those peaks are removed, and the values are better comparable with the latter product. We can also look at the histogram of the cost function before and after the removal of source cloud. So after we remove the source cloud, we can see the distribution is much better than what we have before, which also comparable to a chi-square distribution. So here we can look at the fitting residual again. We notice that the fitting residual rarely look like random, which suggests that there may be some angular correlation in the uncertainties. However, this is really challenging task to calculate the exact amount of angular correlation from this measurement. So we made a few attempts to understand how the angular correlation impact the measurement. So we have assumption that the non-diagonal terms of our current matrix can be represented in this way. And here we introduce a parameter called the correlation angle. And based on this, we can also generate synthetic errors and with different value of correlation angle. So when the correlation angle is small, we have data look like this, but with larger values, we see they start to have a longer range of correlation. And then we can add those errors into the simulation and study how that impact the retrieval residuals. As showing you here on the bottom, we can see the one with longer range of correlations seem like have some error removed. So this clearly indicates some overfitting. So it will have impact in the retrieval uncertainties. And another mystery is how much correlation is really there in the real data. And to understand it, so we compute our correlation from the fitting residuals. And our estimation is that the correlation angle is probably larger than 10 to 20 degrees for reflectance. And there's a smaller value for degree linear polarization. So you can find our study from this from the preprint in the AGU fair, which is publicly available if you're interested in the details. So in summary, uncertainty analysis is useful to understand retrieval performance and guide the improvement. And if you're interested in PACE data, we have 1 day of HARP2 simulation available here. And you can also find the SPEX1 simulation, which is done by iStrong team in the same link. So I will stop here. Thank you for your attention.
So thanks, Gao. I think we're going to move on to the next talk. This one is by Chia Ping Cao, retrieving water vapor profiles in clouds in microwave and infrared visible spectrum.
Hi everyone, my name is Jiabang Guo, and today I would like to talk about retrieving water vapor profiles and clouds. And I would like in this presentation, I will focus on microwave and infrared, but not including visible channels in these retrieval works. And before my talk, I would like to acknowledge my co-authors, Chris Kummerow and Stephen Ryden, for their help to this project. And I also want to thank the session chairs for giving us this opportunity to do this presentation. And first, I would like to introduce what is Tempest mission. Tempest is for temporary experiment for storms and tropical systems. The concept of this mission is to launch a constellation of 8 microwave CubeSats in a single orbit, providing microwave measurements from 89 to 182 gigahertz. And this will give us the evolution of the water vapor and precipitation about 20 minutes. And also give us the relationship between water vapor and deep convection in the tropics and mid-latitudes. This before fully launched of the CubeSat, Tempest D was launched in 2018 to demonstrate the ability of the CubeSat. As we can see from this figure, this CubeSat perform pretty good. The ocean and land are distinguished, separated, and we can also see the distribution of cloud. However, in 2021, the Tempest D was deorbited. Next, we have new sensor. Yeah, the new mission called STP-HN mission. And STP-HN was launched in 2021 and is a testing platform on ISS. This platform carries two sensors. One is copper, providing low frequency channels from 18 to 33 gigahertz, and also Tempest, providing measurements from 89 to 181 gigahertz. In order to test our retrieval algorithm, we use simulated Tempest D observation over ocean. And since Tempest D provides 5 channels of observation, we use optimal estimation given that temperature profile and surface temperature and emissivity from EIA5, then we can retrieve 5 parameters, including 3 levels of water vapor profile and 1 level of water cloud and 1 level of ice cloud. Those 5 parameters are simultaneously retrieved. And this is an example of the cloud profile extract from EIA5. As we can see, the original cloud profile are quite complex. In order to test our algorithm, we simplified the cloud profile into single level of water cloud and single level of the ice cloud. And this is the result by using simple cloud profiles. And we also know the cloud top height. And this is result for retrieve water vapor. And x-axis is the difference between water vapor, retrieve water vapor, and a difference between retrieve water vapor and also water vapor from EIA5 over pressure. As we can see, since we only retrieve 3 levels of water vapor, the black solid line is the mean error. Mean error is zigzagged, and also the blue shaded line is the standard deviation, also zigzagged. And next figure is the result for water cloud. As we x-axis is the total cloud liquid water path from EIA5, and the y-axis is retrieve value. As we can see, results quite good 1-to-1 relationship, and R-squared value is almost 0.9. And this is the similar result for ice cloud, and R-squared value is 0.8. It's not bad. And next question is there any way to improve the retrievals? And the answer is yes. We take observation from GOES 16. GOES 16 provides observation from visible to infrared, and we use channel 8 to 10 provide IR channels from GOES 16 and to include to our optimal estimation algorithm. Then we can retrieve more water vapor profile from 3 levels to 6 levels. And the upper figures are the results by using only 5 Tempest microwave channels, and lower figures will be 5 Tempest plus 3 ABI IR channels. And as we can see, the retrieved water vapor significantly improved, less zigzag, and the bias is very close to 0. And next figure is result for water clouds. And results are about the same before using IR channels. But iCloud getting much better. R-square value increased from 0.8 to 0.96. However, those results are based on the simple cloud models. What will happen in the real world? I mean, original cloud profiles. And the upper three figures are the result by using simple cloud profile, and we also know the cloud top height. And the middle three figures we use the original cloud profile, but we still know the cloud top height. And the last three figures are using original cloud profile. But since we don't know the cloud top height in retrieval, so we have to set a certain number. So we set water cloud top height at 900 hectopascal and the ice cloud top height at 300 hectopascal. And as we expect, the retrieval error increase, like for water vapor, it increased for about 0.5 to almost 0.6 gram per kilogram. And the water cloud retrieval about the same, although it still decreased from 0.89 to 0.83. And for ice cloud, it's about decreased from 0.96 to 0.88. Next, this will be my summary and what we will do in the next steps. The cloud top height affects more for ice than water clouds in retrievals, and adding 3 IR channels from Go16 significantly improve the water vapor profile retrieval and also ice cloud retrievals. And we are going to test our retrieval algorithm using observation from temperature on ISS. And is there any way to improve the retrievals? Yes, we plan to add more information from other API sensors and also use cloud top height and cloud phase product from Go16 and use lower frequency channel from cover to provide more sensitivity around the ground. And also use a series of the temperature observation provided by INCA's mission, which will be launched in 2027. I will stop here and take any questions or comments.
Any questions? Okay, well, I guess we should move on to our next speaker. Thank you. Our next speaker is Pingwang Zhai. He's going to talk about a unified radiative transfer simulator for hyperspectral radiometers and polarimeters.
Good afternoon. Thank you very much for staying late and be with us. I will talk about a radiative transfer model that we have been developing years. So I wanted to acknowledge my co-authors from NASA Langley Research Center, NASA Goddard Space Flight Center, and my students. So I skip this one. So main motivation of this work is I'm involving the PACE mission, which will carry these 3 instruments, including OCI, HARP2, and SPEX1. So OCI, it's a hyperspectral radiometer. It's a single viewing angle, but very lots of spectrum information. For the 2 parameters, you have less spectral information, but with multi-angle information. So the question is, how can we build a reliable forward model, which can simulate the spectral response of all three instruments with the same microphysical properties. So that basically with a different measurements, you all point to the same microphysical properties. With that, the strategy is that we, based on a monochromatic multiple scattering radiative transfer model, the core features of the model are include the exact atmosphere ocean coupling and polarization, flexible atmosphere and ocean properties. It also have newly added improved pseudospherical treatment of the Earth's atmosphere. We include the effect of gas absorption. You see the molecules here, and I will talk about how do we do that exactly a little bit later. So here I cover the physics of a monochromatic radiative transfer model based on successive order of scattering. So you have the atmosphere, light comes in. We know the single scattering very well, and at the interface, it's reflected and transmitted. We know the ocean roughness based on wind speed, so that we can get the reflection and the transmission based on the reflection and the transmission matrix. And in the atmosphere, the reflection light can be calculated based on this one. And in the ocean, the transmission is also calculated. So the ocean bottom also have reflection. So based on this, we do iteratively, we just need to solve a set of angular integration and optical depth integration equations. Talking about how do we convolute the gas absorption with the scattering, I take an example of the strong water vapor absorption band. In this band, you can see it's very dense. If we do monochromatic hyperspectral line by line simulation, this is going to be very, very expensive. So in order to resolve this, we use a parameterization scheme. Basically, we parameterize the readings field as a function of absorption optical depths. So within this instrument line shape function, which is showing by this orange this orange curve here, we select several channel and calculate the readings field, and using this parameter equation and solve the unknown parameters, so that we can get a full representation of the readings field within this band. After that, we convolve it with instrument line shape function. I also include the inelastic scattering process in the ocean water. For example, here you see this one, it's the excitation wavelength is here. Then you see this Raman scattering of ocean water and the fluorescence of the yellow matter in the ocean. And if you move this excitation here, you see how they shaped. So so in the model, we consider all the excitation and the emission relations properly. And this shows the feature of the CDOM or yellow matter fluorescence features. We use this information to model the inelastic scattering. A newly added feature, as I mentioned, that we use the improved pseudospherical shell algorithm, which give you better dependency in the spherical shell. I will not talk about the technical details, but if you are interested, feel free to let me know. I'm going to show a few applications of the model. For example, here, the top left figure, you see the total reflectance at TOA for different chlorophyll concentrations. You see in this range, you see the difference based on different chlorophyll concentration. So that's all the ocean color remote sensing is based on. But if you look at the polarized reflectance, the difference is much smaller. That means that polarization information is very limited for ocean color remote sensing. However, if we use the polarization information to characterize the aerosols at the atmosphere, so that we can do better atmospherical correction. Another application is that to characterize the chlorophyll fluorescence near this peak. So you see for the different chlorophyll concentration, this peak is higher. Actually, the true fluorescence peak happens at 685. But 685 is diminished by oxygen B band absorption, so it doesn't show up in my curve. Instead, we choose this 680. Another application is that we model the instantaneous photosynthetically available radiation IPRA. So we calculate this IPRA for a flexible conditions of atmosphere and ocean. And this matrix is generated by my student Kamal Ariel. He studied the different atmosphere and ocean conditions, what's their influence to the IPRA. Another application is also done by Kamal Ariel. This work, we use the model to study the ocean water limit readings. What's the angular dependence of water limit readings? This has a great application in the ocean color remote sensing. This application is that the radiative transfer model can be used as a forward model of retrieval algorithms. This it's a busy slides, but I'm going to skip it because luckily previously Mongo talked about maple and fast maple. That's the same model we are talking about. I wanted to highlight a study that my student Naranga Hennadige, her work, she studied this different bioptical model showing C1P1 here and C2MP3 and C2MP7. Basically, this is a 3 different bioptical model of the ocean waters. The C1P1 is typically used to characterize the open ocean waters. The message here is that you see the chi-square, which is the cost function. The C1P1 model does not give you a good converge. The other multi-parameter model give you a better converge, but the performance is similar. So this MP7 means more parameters in the ocean water. More parameter doesn't mean it's better. So she's wrapping up her PhD study. If you have an exciting project, wanted to hire a talented young scientist who knows very well radiative transfer and inversion theories, feel free to let me know. In the end, we have this decade-long effort developing a radiative transfer model, which have basically all the features that we can think of right now, from 300 nanometer all the way up to 2 micron within this span. If you have any comments or feedback, please let me know. I put my email address here. Thank you very much.
Questions, please?
Hi, Penwan. Thanks for the informative talk. I'm interested in your pseudo-shell radiative transfer model. So I'm wondering, despite the difference of the assumption of the pseudo-shells compared with plane parallel, is there any other differences compared with other typical radiative transfer model like this sort? Because I'm wondering this because the pseudo-shell assumption may be a good application for the day-night band in the VS for the lunar radiative transfer model, because the moon-Earth distance are quite not suitable for plane parallel assumption. So I'm wondering whether the radiative transfer model can be used for that. And yeah.
Sorry, I wasn't sure what I asking. So the plane parallel and the spherical shell will have differences, but what is your question? Sorry.
My question is, despite the differences between the plane parallel and the pseudo shell, what will there any other differences?
Yeah, mainly in the polar region, region that you have very large solar density angle. And also the viewing angle, if the viewing angle is larger than 60 degree, the spherical shell effect is very significant. So mainly this can improve the polar region environmental remote sensing.
Okay, maybe we can talk later. Yeah,
Thank you.
thank you.
Yeah.
And if I understood right, when you accounted for filter function integrating over line of absorption, you didn't use K distribution like I would anticipate, but instead you use just few lines and then integrated. Can you comment why you do that? And
Yeah, actually, Dr. Xu Liu earlier mentioned a few caveats of K distribution, including inhomogeneous vertical distribution and the gas mixing. If you have several types of gas mixing there, so the K distribution it's not ideal. So this parameterization actually is called double K distribution, originally developed by Qilong Ming. The idea is that no matter what is the vertical distribution, once that's set down, once that's fixed, and then you have different gas all occupy, that we can parameterize the readings field as a function of gas absorption optical depths. So that's we can use a few parameters to represent the whole spectrum. That's the idea there.
okay, thank you.
Thank you.
And next presentation should be in person but online by Vijay Natraj, and it will be the two-stream exact single scattering radiative transfer model.
Are you able to hear me?
Yeah, we hear you, but we don't see your presentation. Could you share?
Yeah, give me 1 second. It says for some reason, okay, I might have to quit and re-log into Zoom. Just give me a minute. I'm trying to share screen again. Sorry, I don't know what happened. Let's see. Can you see my screen now?
Yes, please make it in the presentation mode, and this should be fine. Then. Yeah, it's good.
Does it look okay now?
Yes, go ahead.
Okay. All right. All right. Thank you, Oleg. And thank you to the conveners for giving me an opportunity to talk here. I'd first of all like to acknowledge the co-authors listed here. So I'm going to talk about this two-stream exact single scattering or 2SESS radiative transfer model. This is a product of about 15 years of work. Okay, so first the motivation. As we know, radiative transfer models are required for a variety of remote sensing applications. For example, if you want to simulate radiances from ground-based airborne satellite platforms, you need them. In retrieval applications, you also need them to calculate Jacobians, which are basically derivatives of the radiance with respect to geophysical parameters of interest. And then when you consider OSSIs or observation system simulation experiments or climate models, these require a lot of RT modeling over wide spectral ranges. The problem, as we know, is that radiative transfer calculations are computationally expensive. Now we have new generation low Earth orbiting and geostationary satellites that are expected to generate larger and larger volumes of data. So there's obviously a need for fast radiative transfer. Now, when we talk about a two-stream or 2S approximations, these represent the angular dependence of the intensity in terms of two functions of optical depth. These have been a popular alternative to numerically more precise models, especially for the calculation of fluxes and heating rates, relevant to climate modeling. The nice thing about 2S methods is that they avoid the complexity of numerical solutions to the radiative transfer equation by yielding closed form analytical results. So a number of 2S approximations have appeared in the literature. For example, the book by Radiative Transfer in the Atmosphere and Ocean by Stamnes et al. Has a good review of these approaches. I'll just say that these include, for example, the Eddington approximation and the delta Eddington approximation, where the forward peak of the phase function is represented by a delta function, and the rest of the scattering hemisphere is treated by a two-term expansion. There's this paper, a classic paper by Meadow and Weaver, which kind of presented a framework to unify a bunch of 2S approximations. And also there's been work to extend this to inhomogeneous atmospheres. The main issue with 2S models is that they are not accurate enough when radiances, rather than fluxes or azimuthally averaged intensities, are the quantities of interest. So the methodology used in this work to improve computational efficiency is to separate the radiation field into single and multiple scattering components. This idea was actually first proposed by Min and Harrison in 2004. In this approach, single scattering is computed accurately and multiple scattering is calculated approximately. And the logic behind this approach is that the single scattering calculation, which often captures a large fraction of the angular dependence of the radiance, is fast. Most of the computational effort is actually spent on calculating the multiple scattering contribution, which has smoother angular variation. So the net result is that if the multiple scattering is computed using a fast approach, approximately, the overall RT calculation would be much faster. So of course, the simplest method to do this would be to use the two-stream approximation for multiple transfer. So hence the name 2SESS, the approximate two-stream multiple scattering coupled with an exact single scattering. So a brief comparison of 2SESS versus other existing schemes. So the two-stream radiative transfer, of course, is simple enough to be solved analytically. And here we adopt the same techniques as used by other authors. So for example, finding particular integral solutions in the way that we typically do for solar or thermal scattering, with exponential dependencies and so on. For the solar case, the use of the average secant formulation for solar attenuation follows the practice adopted, in the numerically precise LIDOT and VLIDOT models, which many people use, using the well-known pseudo-spherical approximation. To the best of our knowledge, the use of a Green's function solution in the two-stream model is new. Of course, we do base this on the treatment that is there in the LIDOT model. In terms of the ESS model, the main new approach here is with the use of a quadrature scheme to solve the single scattering radiative transfer equation in a fully spherical geometry scenario. Now, the 2S model determines the complete, so the single and multiple scattering field, discrete ordinate field, obtained from the truncation of the phase function implicit in the solution method. However, for the post-processed, that is the radiation field in the user-defined direction, only the multiple scattering part of the field is evaluated. Indeed, the post-processed single scattering part of the 2S field is ignored because it's based on severely truncated phase functions. And instead, we replace it by a fully accurate, independent result from the exact single scattering or the ESS model. This is based on the full phase function and is not subject to the limitations of plane parallel scattering. Now, if you think of the computational efficiency, there are many reasons why the 2SESS model is attractive. For example, the ESS calculations do not involve any matrix inversion, which of course is typically the most significant time sink in solving the radiative transfer equation. Also, the layer homogeneous and particular solutions are obtained analytically. And then the boundary value problem, which of course is numerical, has a special structure, which means you can solve them using a pentadiagonal solver, which is far more efficient than the matrix routines used for multi-stream scenarios. So the table here shows the mean computational time for LIDOT in two-stream mode, and 2SESS calculations for realistic scenarios in both the solar and the thermal spectral regions. So roughly you can see, we have on the order of several 100,000 monochromatic calculations. And you can see that there's an average speed up of about 2650 for the solar beam scenarios and 2800 for thermal emission scenarios for 2S ESS with respect to LiDAR. And further, the 2S ESS is about 8 and 20 times faster, respectively, than LiDAR in two-stream mode for the same scenarios. And this demonstrates the impact of using analytic formulas for the two-stream calculations as opposed to the matrix computations used in numerically exact models, such as the LiDAR in two-stream mode. Now we evaluate the accuracy of the 2S ESS model first for a series of slab problems. So to do this, we perform calculations for a range of geometry, optical depth, single scattering albedos, phase function asymmetry parameters, surface albedos, this kind of stuff. Overall, there's about 1.5 million parameter combinations. And we do reference calculations using LiDAR with 64 discrete ordinate streams in the half space. We also perform comparisons with what we call a full 2S model, in which the complete radiance field is computed using the two-stream approximation with no exact single scattering here. So the results are shown here for upwelling radius at the top of the atmosphere. And you can see that the 2S ESS model does much better than the full 2S model, as shown by both the coefficient of determination and the Pearson correlation coefficient. And you can see the same thing for downwelling radiance at the surface. Again, the 2S ESS model far outperforms the full 2S model. You can also see that the upwelling full 2S results are more accurate than those for downwelling. And this is a consequence of the assumption of a Lambertian surface. You can see the results for this more clearly here using this PDF plot, for downwelling on the left and upwelling on the right. Again, you see that the full 2S, which is in blue, deviates a lot from the exact results, but the 2S ESS matches the LiDAR calculations really well. Now we can do the same for more realistic multi-layer scenarios. For this, we use the WRF-Chem model to generate, trace gas mixing ratios, aerosol concentrations for a variety of aerosol types for about 200 different, scenarios representing different regions, seasons, times in the continental US. So these cover a range of solar and viewing zenith angles, going nearly up to almost 90 degrees solar zenith angle and 60, 70 degrees viewing angle, variety of aerosol optical depth, surface albedos, and all that. And we do top of the atmosphere radiance calculations in the shortwave infrared on the left and thermal infrared in the right. And across all these profiles, you can see that the errors from the 2S ESS model are on the order of about 0.1% in the shortwave and about 0.01% in the thermal. So the model is performing pretty well. So just to quickly summarize, the 2S ESS model is generic, flexible, and computationally efficient RT model for vertically inhomogeneous media that accounts for spherical geometry effects. We have performed detailed comparisons of the accuracy for both slab and multi-layer scenarios. The errors are really low. This model significantly outperforms the full 2S model. I didn't have time to show it here, but we've actually made comparisons against the test cases that come with the popular DSOT code. And more importantly, the code is fully linearized. You get Jacobians, analytic Jacobians, which are useful for retrievals, and Jacobians with respect to any surface atmospheric parameter that you're interested in. And the last slide here, this work was recently published in JQSRT. You can find a lot more details about the theoretical basis of this code, and also about more discussion about all the results in this paper, for which I provide the details here. The code is publicly available on GitHub. The data relevant to the tables and figures in the paper can be downloaded from Zenodo. And most important, this is publicly available. Please use the code, improve it, share it, and provide feedback. So thank you very much. I'll be happy to take any questions.
Questions? Jacek.
Hi, Vitra. Very nice. Thank you for the presentation. This is Jacek speaking. So, Mike Mishenka has shown that if you have, for instance, 2 orders of scattering, then ignoring or taking into account polarization can lead to significant changes in the top of the atmosphere radiances. And 2 or 3 orders of scattering would then be approximated by your two-stream method. So my question to you is, if you are interested in polarization or in studying the effect of neglecting the polarization, how would you do that with a two-stream model?
Yeah, that's a good point. So I have to state that this particular model is useful for scalar scenarios and not including polarization. That's for sure. Yeah, you cannot represent polarization with two stream. You need a minimum of 4 streams. So this is mostly intended, where polarization effects are not that significant. Also, I didn't have time to go through this. There are obviously cases where this code does not work the best. For example, when there's significant aerosol loading or very thick, optically thick clouds. However, I think for those cases, for example, for optically thick clouds, you can use diffusion theory and analytic formulas therein. For the thick aerosol scenarios, you can couple this 2S ESS model with a PCA-based technique for which we have published some papers before as well. But the issue of polarization is a little bit different. That one, yes, the 2S ESS model cannot really do that well enough. So that's a good point.
And Vijay, I also have a question. Could you just clarify one more time? Would your method would be accurate enough to calculate polarized radiances and then polarized intensity on the top of atmosphere like we do in satellite retrieval?
No, for the polarized radiance, it won't be the most. First of all, it doesn't calculate polarization except in the single scattering approximation. So that's not going to be good enough. But like I said, for radiance only applications, I think it is going to be pretty good. Unless, of course, you go into the deep UV, then even the radiance might have some, impacts, even if you don't consider polarization. But if you're talking about shortwave infrared, thermal infrared, I think in these regions, the code will be pretty useful as long as you don't need polarization.
Okay, thank you very much for clarification, and it's time to move on.
Thank you.
So our last speaker will be Masa Mamoy. He's going to talk about comparison of efficient computation methods for the polarized plane parallel radiative transfer, including solar auroral regions using the GRASS platform.
Thank you. I'm Masahiro Momoe from GRASS. I will talk about the truncation problems for the auroral and sanguine regions. So I can skip these steps because everyone knows the reason why RTM is required. The accurate radiative transfer is necessary for crucial for the retrievals. So I will skip, and I will show the basic analysis for the radiative transfer for the under aerosol radiated atmospheres. So under the aerosol radiated atmospheres, because of the forward peak radiance, forward peak phase matrix, we need large Fourier decompositions for reconstruct the radiance field. So, but this need a large computational resource, power of the 2 or 3 in the discrete ordinate method. So, and for example, in the aerosol radiated atmospheres, especially that case, we need 100 Fourier decomposition order, and the cloud atmosphere rather than 100. And then this takes 1 hour or sometimes 2 hours, depending on the case. And for example, small numbers we used, this makes the errors in the forward regions. It's caused by the truncation, truncated by the Fourier forward peak. So then we need additional treatment for the forward this truncation part. Then in the past 30 years, many scientists try to consider these questions, these terms, the correction methods. So most of the papers that use the perturbation theory, radiate transfers come from the real radiate transfer and the truncation space. And one of the paper work on Elman used in the truncational space, and another is based on Nakajima and Tanaka, and recently two papers for polarization radiate transfer and the 3D radiate transfers use taking account every component of this perturbation radiate transfer. And using this correction method, we can reconstruct the radiance field. And this shows the difference in the radiance for downward and upward. And in the vacuum element, this has still errors in the forward peak, forward regions, but using the IMS method from the originally Nakajima and Tanaka can reconstruct the radiance field both for downward and upward. So this is for the this is take account errors of forward peak. So then it is available for the land surface. But one question is, what about the sanguine over ocean? Like these white regions. So even with taking account, aerosol part is taking account, this has still errors in the sanguine regions. It is this red point. So then, because the sanguine has a strong peak, then in this study we try to take into account this sanguine effect, and for the second order of the sanguine effect. And for the second order, we can think the two patterns. One is before surface refractions, or under the after surface refractions, they're scattered in the atmospheres. And then in this study, we only consider these centers, this before surface refraction patterns called the PIMS with sanguine corrections. And using these sanguine corrections, especially in the bottom of the atmosphere, this oscillation in the sanguine region can be suppressed and well reconstructed in the even with small number of the Fourier truncation orders. And well, I should explain the figures. So the left part is without sanguine corrections. It means that only atmospheric term is corrected. And the right part in the additionally correct the sanguine effect, the second order of the sanguine effect. And the bottom is the bottom of atmosphere, and the upper side is the top of atmosphere. So then in the bottom of atmosphere is very reconstructed using the IMS with the sanguine correction. And even with the at the top of atmospheres, this fluctuation is decreased and improved the radiance. But Wacky and Ehrman had we didn't sanguine corrections with the Wacky and Ehrman, and then this had a 2% errors, sometimes to have 2% errors in the sanguine regions. So finally, we try to apply the observational data of the polar observational data in the open ocean site. So we try three patterns, three setups. One left to set up is without sanguine corrections, and the right side is with sanguine corrections. Then using the sanguine corrections, the computational burden is increased. It means the computational time is also increased. But compared to without sanguine corrections with the large truncational order, like 20, this with sanguine correction is still faster, like 8 times to 10 times faster than this without green corrections. Then about the score, regarding to the score, most of the scores, for example, correlation coefficient or root mean square and the number of the J-cos criteria is also improved. So then this is the summary. In this study, we compared to the correction methods of the truncational problems, and we newly developed the correction method for the sanguine truncations. And then both of the method is compared in the GRASP algorithm, and we also apply to the observational data. Then we get the improvement using the sanguine corrections for the polar retrievers. That's it.
Thank you. Questions? So is it implemented in the GRASP algorithm on GitHub? Can we use it now? It's available. Great.
Well, GRASP is open source, so of course.
Right. Any other questions? All right. Any concluding?
Okay, thank you very much, Masahiro. And on this, our session arrives to the end. And again, I think thank you very much for staying that long. The best is for the last. And hopefully to see you again, probably next year on other conferences where we will try to also organize something interesting. Thank you very much. And let's give maybe one more upload for presenters. And we can conclude. Thank you. Yeah.